The only thing between you and your coffee is Alejandro. Alejandro is giving also a short talk about modules. I knew you would like that. So Alejandro, excuse me, Alejandro is going to tell us how, more or less accidentally, Sonar became a build system. Yeah, this is what he told me. Go ahead, thank you.
Okay. Thank you for putting pressure on me about the coffee. I will try to be brief. So, about me, I'm going to go closer. So, I'm Alejandro from Spain. I did my master and PhD in the University of Cádiz for the 22% who are not from Spain, that's on the south. I'm one of the 22% who are not living in Spain right now. I'm based in Geneva for 17 years now. I'm working at Sonar. I will talk about them now, on the C Family Squad. And I work on the adding support to C++ 20 modules. Before that, I worked on the astronomy department, University of Geneva, so that was scientific computation. And before that, data transfer at CEN. So Sonar, what we do is analyze code. We are code quality and security. How many people use analyzers? Any. Can tidy code. Oh, nice. Quite a lot. So we support a bunch of languages, C++, obviously, otherwise I wouldn't be here. We are spread. The main office is in Switzerland, which is where I am located. And we have, if it rings a bell, SonarQube, or Community, Server, Cloud, and Friday, previously known as Sonar Cloud and Sonar Lead. I have put a little C++ icon next to the last three because in Community, which is open source, there is no C++ support. So about this talk, this is not going to be a tutorial on modules, just to be clear, nor about experiences of ourselves using modules, because we don't. If you want to get started on modules, I put there a nice talk from last year from Andrea Base. I will though give a brief overview to get a sense how many people at least wrote a hello world using modules. Not many. Something more complicated than hello world? Okay, so it will make sense to go through a brief refresher. It's going to be very shallow, okay? Just to be clear. Well, I'm going to be redundant with the way C++ code before C++ 20 was structured. With your header, I didn't have space for the guard, so I put a pragma once, where you have the declaration, then you have your definition on a separate translation unit, on a CPP, and then well, you have your another translation unit, another source file where you call your function. And then the nice thing is that you can compile both CPP in parallel. They are independent, they share the header file, but you can just, if you have two cores, you can compile both of them at the same time. And if you have 1,000 and you have 100 cores, then you can compile 100 in parallel, which is very nice. Very simplified version of modules with a single module unit. So now you can have the declaration and the definition within the same file. So you have, I will talk about this part later, the module here saying that this is a module unit. You include a header, you export your module, you have a namespace, and I'm exporting the version function. And now here you don't include and you don't import. I'm aware you can do import std in C++23. I'm also aware you can do import std in C++20 with the three major compilers, but I wanted to highlight that with Clang and MFBC, you include and then you import. If you import and then you include, it may break very badly. It shouldn't, but it does. It has something to do with the way they merge the declaration for both. If library is depending on IOStream, you can get into trouble when they are trying to merge both declarations. So it shouldn't matter, but it matters. So I wanted to highlight it. And the pity now, we have two files, and we can only compile one at a time. Because in order to do the import, you need to build the CPPM, the module, before. So there goes your parallelism. So about some terminologies, some of these words I will reuse later on, so that's why I want to go through the terminology. So the global module fragment is what you have between the module keyword and when you introduce your module. So anything here, which can only be preprocessor directives, so include, if def, and the like. So primary module unit, you can only have one per module, but you can have multiple files per module. So this is where you, where you export your name module. And then you put a bunch of declarations which may be exported or not. You can split, like we used to split with headers and CPP file. You can split your implementation in a module implementation unit where the export word is gone. So now this is an implementation unit. Whatever is inside is not visible anymore to the importer. In this particular case, I'm importing, this is actually a typo because I'm not exporting, importing in this case. Two partition units, which look like this, almost like a module interface, but where you have the identifier, a semicolon, and some other name. You can only have one level of nesting, so you cannot have identifier column, identifier column. Private module fragment is something you put in your module interface unit, module column private, and what is here is not going to be reachable or visible. I say what that means now, to the importer. Doesn't work on GCC. So if you want to use multiple compilers, you cannot do this in GCC yet. Okay, so 3 keywords, which is attachment, module linkage, which was mentioned this morning already, and the ownership module of the module linkage. So I could look here. Attachment, when you declare something inside after the introduction of the module, the name module, the declaration is attached to that module name, except if you use extern C++. In that case, it's attached to the global module, like if it was before module. So in this case, flags, note I haven't put any namespace here, but namespace and modules are orthogonal. Okay, so these two are on the global namespace, but they are attached to the parser module. So this one doesn't have an export, which means has a module linkage, again, like was mentioned this morning. And usually the name will have the module name as part of the symbol. So the linker will know that these flags in this module and these flags in this module, even though both are in the global namespace, they are not the same. So everything is fine. Then this one is exported. So it has external linkage. And thank you for the introduction about linkages this morning. It is attached to parser nonetheless. It is on the global namespace, which is bad practice, but I did it for the sake of example. Here we have another collision, which is also attached to serializer. It's also on the global namespace. And now this is where the ownership model comes in. In the strong model, the linker will see the name with the module as part of it. So if you use the same, this one from this module in one translation unit and this one from another translation unit, it's fine, the linker can figure it out because the name is part of the symbol. If you do import both from the same, then it is a problem. You're breaking there is an ODR, but it's fine because the compiler will be able to diagnose and tell you. This is the strong. In the weak model, the module name is not part of the symbol, and then you will have ODR violation. Luckily, it's seen for once the 3 major compilers converge on strong. So you should, if you use a modern compiler, it should be fine. They all going to keep the module as part of the symbol, so there will be no ODR. Another 2 keywords, visibility and reachability. So visibility is the importer can name it. So that's when you have something with export in front or inside something with export in front, like in this case, create parser is not exported, but the namespace is, so you can name it. That means that if you import a parser, you can name parser, create parser. This one and struct handler, they are not exported, you cannot name them. So the importer cannot refer to them. They cannot say handler or parser handler, there is no way they can name it. But handler is nonetheless returned, so it's reachable because the compiler needs to know what the handler is, what there is inside, what the memory layout. So even though the importer cannot name it, it can use it without, like you would with a lambda or with a struct defined inside that function. So a reference to Daniela, who made a talk in 2021 about the three. She will talk about this she talked in the past about this in way more detail. Outside of the language itself, there is BMI, which I'm going to use a lot, which is binary module interface, and CMI, which is exactly the same thing, but with a different name. Basically, when the compiler compiles a module, it will generate two binary artifacts. The object file, which is going to be used when linking, and a BMI, which is basically a memory dump of its internal representation of the DST. Internal representation of the DST, which means they are not portable and they cannot interoperate between them. The slightly change when you generate a BMI breaks everything. You cannot use a BMI generated by GCC with Clang, not even use a BMI generated by Clang 17 with Clang 18, not even within Clang 18. If you change maybe just one little flag when compiling, you break completely. It makes sense because it has to be fast to serialize and deserialize, otherwise there's no point on this. File name and extension, they are basically meaningless. There is some convention and some preferences. So Clang like CCPM or CCM or anything ending on an M. GCC doesn't care, CPP. And MSBC prefer IEXX. So meaning if you don't pass any flag, they will figure it out. They are a module and enable the flag for you. But outside of that, they don't mean anything because you can force them to be module. And you can compile IXX with Clang or CCPPM with MSBC. It doesn't matter. Normally, your build system is going to take care of that for you. Header units, they're a beast on themselves. So we don't support them, for the record. They are not quite headers and they are not quite modules. And I think I'm going to just stop there. Daniel made a very good talk about why they are complicated and why they're actually bad and better not use them if you don't have to and if you don't know what you're doing. Which is unfortunate because I know at least of one user of Sonar who is using import headers. So, the thing that now you cannot compile everything at once means the build system needs to be module aware. It needs to know in which order how to do things. If you have an import, you cannot compile that file until the module it imports has been compiled, which means now you have bottlenecks. You cannot throw all your code at your source and hope it works. They will have to wait each other. As of the current status, I didn't put version because I didn't really know what to put there because partial support, they have had partial support for a while. Should I put the latest or? I didn't put any, just use the latest you can. There are so many bugs lurking on the three compilers that pick the latest and you will be good. Import std, GCC 15, which will be the next one, is going to have it. Clang already has, and MPC also has it. Even though that's C++23, all of them are going to be happy if you use it on C++20. Build system, build 2, CMake, MSBuild, XMake, which I only know CMake and MSBuild for the record. And you can write your own makescript if you want to, but beyond 2 files are going to be very hard. So what do we do to give a little bit more of context? So we analyze C and C++ and Objective-C. We care about C++ here. We are built on top of Clang. We have a fork downstream. We need to know how the code was compiled in order to, which compiler you're using, which standard you're using. When we see a preprocessor directive, what was defined, what wasn't, where to look for headers. I saw a bunch of you use analyzers. If you ever wonder why do we even always ask you to run the build wrapped by a command, it's because of that. We need to spy on you and look how you compile your source code. Otherwise, we don't know really what you are compiling. If we get the define wrong, we might be analyzing something completely different. So we use compile commands. You're aware of it. It usually can be generated by CMake already, and used by a bunch of other tools to know for auto-completion and the like. And well, we can figure out some of this stuff automatically. I will briefly mention that later, because it's going to be important also for modules. They look something like this, and I put here an example of compiling the STD module as generated. Well, I make it shorter because otherwise it was too long, by CMake 4 already, I think I use. So you can see it looks like, well, you have the standard, you have an add, which means this is a file, and you have to read the file and put the content of the file as a command, as a flag. You have the object file, and you have the file you are compiling, telling you where it's putting it. And then this is the file that is importing it. And the content of that mod map is basically this. I'm compiling a module, I want you to write it down here. In main, which is the importer, well, the file for STD is this PCM. So this is the binary dump of the memory of the compiler, basically. Any question about modules themselves so far? Okay, so we analyze C++, and modules are C++, so let's do it. Why did we wait since they have been around since 2020? Well, you probably already know. Yes. Taking a while for things to catch up. CMake was finally non-experimental by the late 2023. Clang 19 was finally branched in 2024 in summer. We needed to wait for this. This is a technicality. Basically means when you dump the AST, Clang before that dump the AST. Meaning you get, if you do include IOStream, it's going to dump IOStream. And if every module does that, then you're going to have huge binary files on your disk. And they don't matter most of the time because they're not going to be reached from the importer. So with this, finally, all those entities are removed from the binary, and now they are a reasonable size. It didn't make sense to do it before. And well, they seem to be catching a little bit of momentum. So it seems like a good time. So first, we need to look for projects to test. So if you go to source graph and look for export module in C++, you get 87 hits. If you query for imports in C++, beginning of line, you get 48, which is not amazing. And I don't know if you know Are We Modules yet. They track a bunch of libraries and projects, and there are 22 out of 2,400 projects that they know of that actually use modules. So, I mean, adoption is not great, and this is one of the reasons it took us a while as well. But there are a few. And finally, some of the results you're going to see are actually from GCC and LLVM and forks that are testing modules. So they're not using modules, they are test files. It's interesting, there are way more export than imports. Like if you export, you would import. Sure. Anyways, we found some which are of reasonable size. Infinity, which is an AI database and use only module. MP units, which is a quantity and unit library, someone mentioned it to me before, which is to be proposed for C++ 29, so definitely makes sense to be able to analyze that. I think simple, there is an experimental branch. They do export a module, but they don't use it internally, and there is a branch where they actually use modules internally. From Alibaba, I believe. A few others, but the three are the most interesting. Like, they are real, they're not toy. So first things first, we need to know, like I said, if you have a module, who is importing who, what is importing what. I said we have the compilation database. I show a very nice example. Simple, can get it from there. So let's look how compilers do it. So in MSBC, so you get the output binary, the source file, using CPPM everywhere, because like I said, it doesn't really matter. Okay, fine, I have the binary name, and here I have the module name, the binary name again. Okay, I can link those. Clang, okay, again the binary, source, module name, binary, importer. Okay, I can link those as well. TCC, Okay, they have one level of indirection. It's a text file with a bunch of module name binary. Okay, I can leave that too. Yes, might work. But MVPC also. Yeah, just write it down in this folder. And just look for them in this folder. So if this actually importing anything, I don't know. Clang, similarly, you can output. Okay, I have the file. And you can look for them in this directory, like if they were an include. Okay. You already need to look at main to know if it's importing something. GCC. Do you see anything about module here? Absolutely no mention whatsoever. And remember, this is an accident. CVPN, because we use CVPN. Actually, it doesn't have to be, it could be CVP. So yeah, implicitly, it's going to go under GCM cache with a given name. GC will figure it out by itself, but we can't. Not looking at the compilation at the compile command. If you use make or something of the sort, most likely you will have one of the long forms, but that's something we cannot tie ourselves to, so we have to scan ourselves. Okay, a complicated thing, but fine. We have to go through all source files, pre-process them, well, that can be done in parallel. You don't need to resolve dependency in order to scan, luckily. Just for the record, it involves only pre-processing. Like, luckily, import and export a module, they are pre-processor things. They don't have to go through the whole parser. So at least it's fast. So even for 1,485 TUs in Infinity, in 7 seconds we are done, with 16 threads. Async simple, less than half a second against 16 threads. Okay. It's a penalty, although can be done. Now we have to scan the dependencies. And we get the list of dependencies. So we have STL, which is this file here, this module is exported by the file, which is importing STL, and this one is exported by this one, which is important. Okay, cool. So now we have the edges. We only need to put together a graph. This is a pet project of mine, which is a little bit more than a hello world, but way smaller than Infinity, which wouldn't fit. And you have the graph. This is an external dependency, which I wrap in a module interface. What is dot are partitions. This is the interface. There should be a main.cpp somewhere there. And there is an implementation unit. So what? Like for illustration purposes. Okay, so we have the graph. As I said, we cannot analyze until we have the BMI because we cannot import until we have the BMI. So at least now we can go and look for everything that is a leaf or doesn't have any dependency, build the BMIs, we are good. Okay, so if you have a lot of core, you're wasting a lot of CPUs there, but that's the way it works. Now, well, candidate CPP not exported, so you actually don't need to build a BMI there. Now, this one, well, you get the idea. Okay, so you might ask, okay, so you analyze as you build? No, actually we build and then we analyze, and then the analysis can be done fully in parallel. We can throw all of them all of the code. Why? Building BMI is relatively fast because we don't do code generation, we don't do optimization, we only need to dump the EST to disk. The analysis is heavy though, so it would be really a shame to stall the whole thing when you are at this point, for instance, and have one single core doing one analysis when you have a bunch of files to do, and maybe they will have to wait for 15 minutes. While maybe only the BMI I'm building is going to be a few seconds, if. So yeah, it was decided better to build everything and then analyze. Like I said, already Infinity takes 2.6 giga space. You have to serialize this somewhere. And this is with the reduced BMIs. So imagine how big that would be if you had everything there. So there's a lot of this space. So what we decided is to have them be transient. We don't cache them because uploading that to the server and then downloading them from the server is going to take a lot of network, going to take a lot of space on the server as well if you are analyzing multiple branches. So they're transient for us. Incremental analysis. So you may wonder, okay, you have one analysis, now modify one file. Do you have to reanalyze everything? Well, no. We look for the file that changed, the compiler, and just analyze that file. Transitivity taking into account includes, obviously. So same thing we should do for modules. If you modify a module, modify a TU, we need to reanalyze and rebuild only what's needed. So let's say I picked this one, obviously, to break my whole thing. Let's say you modify something in this module, which doesn't have a implementation unit. Okay, so that means we need to rebuild those BMIs, otherwise we cannot analyze the file. That means we have to reanalyze those files. Because, I mean, it changed, so now maybe a type is not the same, so we need to reanalyze them, which means we have to rebuild those files. So you can see the complication of modules. Now that a change, it's spread like fire. Almost the whole thing is affected. Again, luckily, rebuilding is fast, analysis is slow. Yeah.
When you change feature-based compilers, do you need to have to do anything with those below feature-based candidates which compilers have?
Regenerate the BMIs. Not reanalyze, but rebuild the BMIs. So the BMI is generating the AST dump into disk, so they can be imported again. Because otherwise we have no representation for the module. They cannot be included textually. You have to treat the AST as the compiler sees it.
So do I understand correctly that bit-traced compilers depends on bit-traced candidates, or it's the other way around?
Yeah, the arrow points compiler depends on candidate, not the other way around. The arrow is to the dependency.
The dependency. So, and you changed something in bit-traced compilers.
Yes.
So, but bit-traced candidates does not depend on bit-traced compilers.
No, and that's why we do not reanalyze, but we need to regenerate the BMIs. So we need to regenerate the AST. Because again, modules are not textual inclusion. And
Okay,
we need
maybe I
binary.
will ask it later, yeah.
Okay, we can discuss it. Yeah, there's a boomer, but at least, like I said, we don't have to reanalyze everything, which is the heavy part. So if you change a very deeply nested module, it's like changing a very deeply nested header that everyone depends on. It will trigger a rebuild of the whole thing. So just, again, the overhead is not that bad. I put MP units there also now for this slide. So for Infinity, which is relatively big, there are 1,500 files. There are only 643 that are imported, so we need to generate the BMIs. Scanning is fairly fast, 7 seconds. Even building 647 is not too slow. Again, we don't do optimization passes or anything, which is usually the very heavy thing. And analysis, however, is fairly expensive, 1 hour, 12 minutes. So all in all, it's peanuts. Not ideal, but well, not too bad. So in summary, we had to scan every single source file, look for imports and exports. We had to build the dependency graph. We have to traverse it, generate the BMIs. When there is a change, we have to track what changed, what we need to rebuild, what we need to reanalyze, what we need to rebuild for what we have to reanalyze. Do this not sequentially, obviously, but actually fill all the cores we can. So look for the leaves that are ready to be built and build them. And yes, if everything is based on modules and we have code generation, we could almost give you a binary already by this time. So it's the title of this talk. We almost became, by accident, a build system. And then this is something I wonder myself, and I have seen a question around. Should we still have a separation between the interface and the implementation? And even though I picked this example intentionally to prove how things can go wrong, I would say yes. Isolate your big implementation outside of the module, because if you change your implementation, you are going to trigger a rebuild of many, many things. So yeah, they do make sense to have implementation units. My takeaway, I say probably because there are always cases where it might not. What about ill-formed programs? You may wonder, well, they're ill-formed, who cares? Well, we analyze it, we care. We cannot just throw it away and say we failed. So we need to be resilient to parsing error. We cannot just throw our hands into the air and say, well, listen, you did something wrong. Why? Well, there are many compilers. I think I overheard you like 200 something. They do have built-in something that we don't know of and we don't support. When analyzing the code, we're going to hit. There are unsupported language features. It takes a while to go after the standard. So obviously, if someone starts using a new feature supported by a compiler that we don't yet, that's going to show up as a parsing error. And then there is SonarQube for ID. You are typing your code. You are going to type things that you haven't implemented yet. You are going to type wrongly a type, things like that. You cannot just fail when you see that. You have to try to recover. I mentioned it before, automatic analysis. Something we do is actually you import into Sonar Cloud your project, click, and it's analyzed. Even though we can get most of the stuff right most of the time, we will get wrong some. So we need to be resilient to the things we get wrong. I'm not going to go into much more detail because this was a huge undertaking by itself, and that will be an hour talk. Fortunately, like I said, we use Clang, and Clang is already quite robust and can handle parsing error pretty nicely. So this is an example of an AST dump of this silly function here. Imagine you forgot an include because you are typing and you didn't type the include yet. You didn't click Alt-Enter to fill it. Or this is a macro that was wrongly expanded, whatever. Luckily, Clang, like you can say, is already pretty resilient. I can say, okay, listen, there is something inside this if. I don't know what it is. So I'm going to put a recovery expression. It looked like that. I couldn't look it up. I don't know. But you get the AST. You still get the return I, you still get the incrementals, you still get the declaration. So you can still do things. And Clang can fortunately emit serialized BMIs even when you have parsing error. You can force it. And it's really do it. Normally it will not, but you can force it. Again, this makes sense also for Clang B or Clang title, which might also find situations where the code is not correct, or not yet, because you're still working on it. Unfortunately, that uncovered quite a few bugs, because in the serialization assumptions were broken. The serializer could handle errors. The serializer assumed many things about those things, and flags were misaligned, and there were a bunch of errors and crash. So we upstream, well, the first one is not from us, but the other two we upstream to Clang. We also found a bug in MP units, which is not related to modules, it's related to concepts, but it took me like a week and a half to debug it, and it's really close to my heart, so I wanted to mention it, because while debugging modules, we had to debug this thing. It was painful, so I wanted to mention it.
Is contributor fixed?
Huh?
Is contributor fixed?
Yeah. Yeah, I did. I'm very happy when I figured it out. It was really a pain. It was really funny. Sometimes you would compile, sometimes you will have a stack overflow, sometimes you will have completely spurious warnings. 1 out of 10, actually. You will get a stack overflow, and it was completely random. Anyways, so what is missing? Import std, we can do import std, that's fine, as long as your build system put the compilation command of import std, like I showed before, we can deal with it, no problem. But then automatic analysis is a different story, because we need where to look for it, and we don't know. We can handle modules if we know where they are. From the point of view of the rule we have, some of them are not aware modules are even a thing. So they misfire. So these two are a couple that actually misfire with modules because they think they're headers. So we need to go through them. We don't support SonarQube for ID. I will say later why. Caching of BMI, I can see how that can be painful and inefficient, even though if the overhead is not too bad, it would be nice to do it properly and allow the user, okay, put the BMI here and I will take care of putting whatever, handling the cache myself. Right now, we do not support multiple builds of a BMI. Like I said, BMI is tied to compilation flags. So if you have a single build for C++ 2326, say, or enabling and disable different flags, you need to have 2 different BMIs. We don't do that yet. And header units, not looking for. But the problem is, like you have seen, and those are queries I did like on last Friday, adoption is really, really low. It's really hard to push forward to actually implement these things. So support for cloud and server, we support is SonarLint or SonarQube IDE. We don't support because it's actually supporting 4 different things, and that's the complication. You need to figure out how to ask this guy here, give me the modules this file is important, give me the modules this file export. Otherwise, we don't know how to put things together. And that's why not, 4 different efforts, not one. I want to mention Tomek, who led the effort, and he was the C++ guru of the whole thing, not me, to be clear. He's now happy at Red Hat working on libstd C++, which is his dream job. Yeah, that's about it. So the key points is there seems to be some momentum, even the thing still needs some pushing. It was quite an effort. It seemed like, okay, what can go wrong? We only need to see what is inside the module. We are writing code to handle dependency and rebuilding and whatnot. Adoption rate, like I say, is still low. It's a pity, or not, I don't know. It's simply a pity. And if you do have modules and you analyze them, we would greatly appreciate feedback. Like, really. So community, it doesn't have to be paying. If you are in Sonar Cloud Free, you can drop a message. We will be more than happy to help. And yeah, a bunch of references there.
Thank you. Questions?
They want coffee.
Looks like they want coffee. So thank you very much.
Good to hear.